Hello, in this video we're going to talk about conjugate acid-base pairs. So, a little bit of review, never a bad thing. So here's the Bronsted-Lowry definition. A little broader. So here, the acid can donate a hydrogen ion, so it donates H+, and since hydrogen plus 1 is really just a proton with no neutron or electron, we call this a proton donor. So the acid can donate protons, then the base can accept protons. So here's an example down here. We have acetic acid, and acetic acid is written this way to show that this hydrogen right here is the one that can be donated, whereas these hydrogens here don't get donated at all. So looking at this reaction, let's define the acids and bases. So the acetic acid on the left, its name is kind of a giveaway. What it does is it donates that hydrogen to the water. And so then the water in this side of the reaction on the left acts like a base because it accepts that hydrogen ion. And then it forms H3O+, hydronium, and the acetic acid negative ion version, which is called acetate. Okay, that's the old stuff. And now here's the new part where we continue to introduce the idea of conjugate acid-base pairs. So here, this reverse reaction also works. In the reverse reaction, the hydronium ion donates one of its hydrogens back to the acetate ion. And in this case, the hydronium ion is functioning like an acid, and then the acetate ion is actually functioning like a base. And so we actually use this as part of our definition. We call them conjugate acids and bases. So here, this is the acid, and then this is its conjugate base. And it kind of makes sense. Hey, I have the same bulk of the molecule, whether it has the hydrogen on there or not, makes it an acid or a base, but it's overall the same hunk of molecule. And then here, this is the base, and here's its conjugate acid. But since water does this all the time, and it's often one of the pairs in a reaction, it doesn't get the glory it needs, so we often just talk about the other part. In this case, the acetic acid and acetate. So to formalize this a little bit, here's another example and a description. So a conjugate acid-base pairs is the acid and the base that's formed after you donate that proton, or the base and the acid that's formed after it accepts that proton. So for this reaction down here, we have ammonia, NH3, and water reacting together. So ammonia is the base because the base is going to accept a proton that comes from water. So one of these hydrogen ions on water comes down and lands on this ammonia. So this goes this way. And so the base is a proton acceptor. The water is the proton donor. So that makes the water the acid, the ammonia the base. And then now the ammonia is NH4+ because it accepted that proton, which then ammonium, NH4+, can function like an acid. It can take this proton, donate it back to the base, and ta-da, right? So this is the base. This is its conjugate acid. This is one acid-base conjugate pair. And then water and hydroxide is the other. One other thing we should talk about is amphoteric ions or molecules, and those can either accept or donate a hydrogen ion. So bicarbonate is an example of this. It can either donate or accept a hydrogen ion. It can even do that with itself. So two bicarbonate molecules, one can function as the acid, one as the base, and they'll transfer that hydrogen ion to make carbonate, CO3 2-, and carbonic acid, H2CO3. And then this happens when you put baking soda in your cookies that you're making. Baking soda is sodium bicarbonate, HCO3, and it'll react with itself. It'll make H2CO3, and then this carbonic acid makes CO2 and water. And hey, that CO2 is what leavens your cookies, or whatever it is you're making. So the conjugate of a weak acid is actually a base, right? So here's our generic form, right? HA reacts with water to form H3O+ and A-. This is the definition of a weak acid and really the definition of a Ka equation. And so, all right, the HA is an acid. It's going to donate this proton to the water. And then, well, the A- is a base. It can accept a proton from the hydronium. And so you have an acid, then it turns into a base, but then the base can do base things, and it can get kind of confusing. So this is what we're here to work out. So you can also write A- as a base in its own equation. And so this equation is the definition of Kb. You take a base and water, and it protonates the base. In this case, it turns it into a neutral species from a negative species, but you still added a proton, right? The proton is donated from this water to this A minus. So the water's the acid, and then the A minus is the base. And then you get the conjugate acid over here on the right. Now, do notice that these two equations are not just the reverse of each other, which means the Ka equation and the Kb equation are not just reversed from each other. Because water is present as a reactant in both of these equations. And then on the right side, one of these is producing H3O plus, hey, that's an acid. One of these is producing OH minus, hey, that's a base. All right, so these equations are not just the reverse of each other, but you can take a weak acid, turn it into a conjugate base, and vice versa. All right, so then now what's the relationship between these two? Well, let's try this. Let's try multiplying them together. I kind of know what the answer is, so that's why I know to multiply them together. So then we take the forms of both of these and throw them next to each other with a multiplication sign, okay. Now the A minuses cancel, and so do the HAs. And so we're left with the product of Ka times Kb is equal to the product of hydronium times hydroxide, which, hey, that's Kw. That's the autoionization constant of water. Like, we know this number already. And so we can make this a thing, right? Ka times Kb is equal to Kw, for sure. Now, mind you, this is not an acid and some other base, right? This is an acid and its conjugate base. You can also do this in terms of P, right? So pKa plus pKb equals 14. Basically, you just take the negative log of both sides and plug the number for Kw in there. So you can do that too. So Ka and Kb for a conjugate pair, remember, acid and its conjugate base, or base and its conjugate acid, you take the Ka and Kb together, they're inversely related. Since they are multiplied equal the same number, or they have to add to the same number, if you make one bigger, the other one has to be smaller. So stronger acids, which means a bigger Ka, have weaker conjugate bases, a smaller Kb, and stronger bases, which would be a larger Kb, have weaker conjugate acids, a smaller Ka. And so this kind of symmetry, in a way, is best visualized in this chart, I think. So let's start up here. So you got HCl. That is a strong acid. So that strong acid, its conjugate base over here is chloride ion. And the chloride anion is pretty much ineffective as a base, right? HCl is so strong that its conjugate base is just, it doesn't do anything. You put chloride in water, it doesn't change the pH at all. It's not a base. Now, kind of in the middle, this is the territory of the weak acids over here. And so weak acids, their conjugate bases are still pretty weak. They're weaker than the acids themselves, but it's not negligible anymore. If you put fluoride anion into water, like say sodium fluoride or something like that, it will make it basic. It is a base. And we get into that in a subsequent video, right, about the hydrolysis of salts and how that affects pH. Right? This comes out to be very important, right? This would be basic in solution. The flip side's true. Here's the domain of the weak bases. That box sucked. There's weak bases. Their conjugate acids are even weaker, but they still function as acids. So if you take ammonium, which is a cation that you can get, right? You can get ammonium chloride, things like that, right? You take ammonium, put that in water, it's going to function like an acid with the Ka and all that stuff, right? Not a very strong one, but it will still do it. And again, that has big implications. And then down here, right, if you have sodium hydroxide or something that's a strong base, its conjugate acid is just useless and does not affect the pH of water at all. So again, this idea is really important. We don't get to it until a subsequent video. Here's a nice table that shows a whole bunch of values, right? The stronger weak acids are on the top, and the stronger weak bases are on the bottom. And there's this kind of continuum again, like we just saw on the last chart. How Ka and Kb, and thus pKa and pKb are related to each other, right? The products of this times this equals 1 times 10 to the negative 14th. The sum of that plus that equals 14 within experimental error. Okay, a couple example problems and then we're done. So which one of these has the strongest conjugate base? Well, what does that mean? So strongest conjugate base means weakest acid. because they're inversely related in that way. And then the weakest acid, well, that has the lowest Ka. So then we just need to look down this list and find the one of these with the lowest Ka. Let's see here, -5, -4, -5, -4. Hey, here it is. All right, so this one has the lowest Ka, and thus it's the weakest acid, which means it'll have the strongest conjugate base. So that's how you would do that kind of problem. And now here's this one. Identify the conjugate acid of HPO4 2- in this reaction. So this one's a little messier, and so we kind of have to dig into this to figure out what's going on. And so, so we're talking about this hydrogen phosphate, this thing. Well, let's see here, PO4. Where do we see PO4 over here? Hey, there it is. Okay, so we found PO4. So now that means these are going to be related somehow. Let me clean this up a little bit. So these are an conjugate acid-base pair. So which one's which? Let's see here. This molecule over here only has one hydrogen. This has two. So in this process, it means that this hydrogen phosphate over here on the left accepted a proton to become H2PO4. And so that means if this is the one that accepts the proton, that's a base. And then this is its conjugate acid. All right, so then that means, if this is a base, that means this is probably an acid. And then that makes sense because this hydrogen right here is going to come off, right? It's an acidic hydrogen. Nitrous acid is a weak acid. And then its conjugate pair is over here. So this is the conjugate base of this weak acid because the acid donates a proton and then you're left with the conjugate base. Okay, so we've sorted out what's happening here. The proton goes from here, boop, onto there. Great. Now, what is the question again? Let's see here, the conjugate acid of this thing. Well, it's a base, so great, this makes sense. So its conjugate acid is that, H2PO4-. And so that's sitting down here, C, H2PO4- is the conjugate acid of HPO4 2-. Okay, so that's what we have for this video. And then further, what happens next is the fact that the conjugate acid of a weak base is legitimately an acid. That will affect the pH of solution. So then we learn how to do calculations of, okay, you put some salt in water that contains the conjugate of something, and then how does that affect the pH? Because that becomes important at times. And so we get to that next. But for now, that's all I got. Thanks for watching.